Hey all. So you've had another couple of days off, or with Churston being closed, and also I thought I'd just record something just so we can finish off the X-ray section of the medical physics topic. So hopefully in the lesson that you've sort of covered today, you've gone through the barium meal, which is obviously quite interesting. It's like you can swallow something, it coats your intestines in some stuff, high contrast medium, and basically that stuff absorbs X-rays. It means you can now use X-ray imaging for the soft tissue inside your body, which is quite fascinating. It's quite amazing. So also on top of that, you've hopefully just looked into the iodine contrast medium. You've looked at CAT scans, CAT being computerized axial tomography. Computerized because it's a computer that sort of manually sort of rotates itself, takes the pictures and pieces them together. Axial because basically it's an X-ray gun or an X-ray tube which is on an axle which goes round in a circle. And the idea of that is it goes backwards and forwards, inside the donut-shaped machine, which you might have looked at before. And basically it takes slices of X-rays through the body, hence the word tomography. Tomography comes from the word tomos. Tomos is the Greek word for slice, hence computerized axial tomography. So now you know about slices, you know about the fact that you can get three-dimensional X-rays, and also you can get it you can either save each image or you can piece them together. So you've got like layer upon layer upon layer over different time intervals to see which part of the brain, if you're taking an X-ray of the brain, is functioning at different times. But what you now need to finish off with is X-ray attenuation. Okay, and there's an equation which is in the form x equals x naught e to the negative mu x, which is in your formula booklets, which you need to basically know about. Okay, so we're going to sort of quickly derive this. We're going to derive it because, well, one, I love deriving clearly, but also because you need to be able to do most of the process just like for the nuclear and particle physics and also the capacitor section. Okay, it's very similar. You should be used to it by now, so it's no big deal, hopefully. All right, but just to introduce it, we're going to imagine that you've got some sort of medium, and it's going to be a uniform medium. So in other words, the density is constant throughout. Okay, same material. So imagine you've just got a load of soft tissue, quite a lot of soft tissue. By the way. It's uniform medium throughout. Okay, and we're going to imagine that we've got X-rays, which are going to come in from this direction. I'm hoping you can see all this. So this is an X-ray. Maybe I should have drawn it wiggly. But the X-ray is going to strike the surface of the uniform medium, and what basically then happens is the uniform medium is going to start to absorb it. So imagine you've got a single photon of light, so an X-ray. If it goes through that medium, the majority of them are going to get through because of the vast empty space between all the actual atoms and nuclei. So some of them will get absorbed, some of them won't. And it's the statistical chance of them being absorbed, depending on the density of the uniform medium. Okay? But what that does mean is if you start off with an intensity of I naught, well, to start off with, you've got 100% of the intensity of light, and that's slowly going to be absorbed over time. But it's not really time anymore, it's to do with distance. Okay? So if we were to sort of just measure this out, and we said, right, every 2 centimeters in real life, every 2 centimeters, each one of these is a distance x, 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 and so on and so forth. Okay, the intensity is going to reduce, so it's going to reduce by a fraction of the initial amount. But imagine you started off with 100 photons, a bit ridiculous, but just go with 100 photons. Well, statistically, those 100, you might lose 10%, let's just say, in the first 2 centimeters of medium, right? So that means you'll be left with 90% of the initial intensity, right? Now, with the next 2 centimeters of depth of this material, statistically, you're going to lose 10% again, because it's just a chance of a photon being absorbed, striking an electron, and so on and so forth, ionizing it. So that means for the second 2 centimeters set, you're going to lose roughly 10% of the 90% that was already there. So you're going to lose 9% now. 10% of 90 is 9. So that means after 4 centimeters, or 2 lots of 2 centimeters, you'll be left with 81% of the original amount. So first off, you lose 10%. The second set, you lose 9%. The next lot, you're going to lose 10% of 81%, so you'll lose 8.1%. The point is, the amount the intensity decreases by decreases. Okay, so this is an equation you don't need to know, but it's R equals mu I. Okay, and this is the intensity. Oh, and you might want to recap what intensity is in terms of power. Okay, it's worth doing that. This mu is the attenuation coefficient. I'm just really hoping you can read all this from where you are. And this is a term which I'm just making up to some extent. It's going to be called the reduction. Okay, the amount that the medium or the intensity reduces by, the reduction. Okay. Now, if you think about it in terms of, or if we think back to nuclear and particle physics, we've got we had all sorts of equations. So we know that the activity of a substance A is equal to lambda n, the decay constant times by the number of undecayed nuclei. Well, that's very similar to this. We've got some sort of constant, the attenuation coefficient, some sort of constant which is dependent on the uniform medium. We've got some number, some intensity, some number of photons, and then we've got the activity. Okay, well, I'm just calling this reduction, right? But the activity, we know, decreases as time goes on for a radioactive substance. So we've got the other equation, which is A equals dN by dt. Okay? Activity is the rate of change of undecayed nuclei. It's how much it's decreasing. And it's got a little negative there. And the negative is there because the activity is decreasing as time goes on. All right? So we're going to do something similar for this. We're going to also say that the reduction is also going to be equal to the rate of change of intensity. However, normally I say that it would be di by dt, but it's not dt because we don't care about time to some extent. We care about the fact that it's penetrating into a material. All right? So it's not dt, it's going to be dx. Hence, we've got an x up here. All right? Okay. Now also, the reduction, as we've just talked about, is going to be decreasing over distance. So now we've got R, reduction is equal to the di by dx. And what we can do is we can equate the two of these. Okay, so if we equate the two of those, in fact, I'll tell you what, pause the video, see if you can derive an equation which is x equals x naught e to the negative mu x. Give yourself 2-3 minutes, see if you can do it. Okay? Tom Nuttall, I'm expecting good things from you. Elliot Owers, good things from you. Peter, pause the video now. Okay, so we're going to say that mu I equals negative di by dx. Right? If you rearrange that so you've got di on the right hand side, I'm going to put dx over here, we get, and I'm going to put the minus over here as well, we get minus mu dx is equal to di over I. Okay, at which point we need to integrate. Okay, and we're going to integrate between two different limits. So we're going to start off with a maximum intensity, we'll say is I naught, and we're going to go to some intensity later on, which we'll say I, which is a function of distance. Okay, and similarly, we're going to start off at a distance 0, we haven't penetrated into the material at all yet, to some distance x. Okay, so then that's going to become mu is just a constant, so it's the negative, so we can pull that out. So we end up getting negative mu x, I'll put the limits back in, x0 is equal to the differential of, sorry, the integral of di over I, okay, which you should all know now because we've done this enough time, it's just ln of I, and our limits, we stick them in again, we've got I and I naught. Okay, so if we multiply that out, we get negative mu x minus negative mu times 0. So that bit there just goes, and that's equal to ln of I minus ln of I0. Alright? Let's simplify it now, then we get negative mu x is equal to, think about the log rules. So the log rules are log or ln of x minus log of y is equal to log, I'm hoping this hasn't gone off the camera screen, log of x over y. Okay, so that's what we can use on the right hand side here. So we can say that it's ln of I over I naught. Okay, and if we want it in an exponential form, we're going to just take the exponential of it. So the inverse of that is the exponential, so we get e to the negative mu x is equal to I over I naught. Multiply that out. I'm just going to put it here now. And it's I equals I naught e to the negative mu x. Alright? So now we've got a form, or a formula, which tells us how the intensity of a medium is going to change depending on, one, the distance that the material, that the X-rays are passing through the material, and this property, the attenuation coefficient, which is related to the material itself. Now, the thing that's going to sort of determine the attenuation coefficient will be the density of the material. We'll just go with density of the material. All right. Forget about the fact that it might change direction. We don't really care about that at this stage, like refraction and whatnot. It's just how much is going to be absorbed. Because don't forget, we'll have some sort of detector over here, some sort of receiver, and that's going to be picking up all the X-rays in that particular range, and it's that we want to be able to experience. So, linking it back to the barium meal, basically, what I'd like you to do is think about whether it has a high attenuation coefficient or a low attenuation coefficient. Maybe use the equation to determine that. Okay, does skin have a high attenuation coefficient or a low attenuation coefficient? What about bone? And how do radiographers use this sort of stuff, use this equation, use a bit of maths, use physics, to determine what intensity of X-rays they should pass through a patient. Alright, I hope that makes sense. Any questions, please give me a comment down below or email me directly. Alright, thank you very much.